So all that's really left out of chapter 9 for us is to talk about some materials that are kind of on the back half of this stuff. So we're talking mostly about water reactive stuff. What we're really talking about in particular here are non-metallic kinds of hazards. So we're going to start with the metallic phosphides. Metallic phosphides utilize the phosphide ion being P-3. And so what we see in these are metallic substances that have reacted with that elemental phosphorus. These used to be used quite often as fumigants. How you would work these is you would basically lay them out in an area that you were going to fumigate. The moisture in the humid air would react with those, form a gas called phosphine, and the phosphine would be a pretty toxic gas. It would be what ends up killing the bugs or the vermin or whatever it is that you were fumigating. Because of its toxicity and because there are just better things out on the market, but these kinds of agents aren't used for that purpose very much anymore. And with good reason. Phosphine is pretty nasty stuff. Phosphine itself is generated when those metallic phosphides react with water. What we get is a poisonous gas. Primary hazard of that gas is its toxicity. That gas does have a particular odor, the odor of garlic or rotten fish. In low concentrations, phosphine isn't terribly hazardous. I mean, long-term exposure to concentrations less than 50 parts per million are known to soften your bones, start reacting with the bones in your body, with some of the stuff in your bones, and making them more fragile. It's when it gets to a concentration greater than 50 parts per million that we really need to worry, because, and we'll talk about this next chapter, there is a class of hazard called immediately dangerous to life and health. And that is the classification that phosphine enters at 50 parts per million and above, where if you have a concentration that high, you can see immediate effects within 15 minutes or less that can greatly impair you and cause your life to be in danger. Another issue with phosphine is that it is spontaneously flammable. And so that is not its primary hazard. Again, the primary hazard for it is its toxicity, but its flammability is also of concern. Another common class of non-metallic agents are carbides. Carbides can come in two different forms. There is the kind of the dicarbide version, C2-2. There is also the C-4 version. This C-2 version is the one that we are probably the more familiar with. This is the one that would make things like calcium carbide, CaC2. Of all the carbides that are available, really only two of them are particularly known to us and considered to be On the more dangerous side, we have aluminum carbide. Aluminum carbide is in one of two forms. It is either Al2C6 or Al4C3. Again, it depends upon which form of carbide we are looking at there. Are we looking at the 4 negative? That would be the one on the right. Or are we looking at the 2 negative, the one on the left? Calcium carbide is also a common one for us. CaC2 is its most common formula. Now, the reason that these two carbides are particularly important is because of how they react with water. So these are classified as dangerous when wet. They are water-reactive substances, and we actually use their water reactivity to our advantage in some cases, and that's why they are commercially important. So the reactions involved for aluminum carbide, we can make it by basically taking aluminum oxide. We talked about aluminum oxide already. Aluminum oxide, Al2O3. That is the most common form of aluminum because of aluminum's reactivity with the air. Well, if we expose it to coke, coke being a commercially present form of carbon, in an electric furnace, the heat of that furnace will basically cause more or less a single replacement reaction to take place, where that carbon is going to insert itself in place of the oxygen. The byproduct of aluminum carbide reacting with water is that we will get methane gas, CH4, and we'll also get aluminum oxide as byproduct. So this is, again, kind of like a double replacement reaction taking place here. And so the primary purpose and use that we have for aluminum carbide is that it gives us a way to generate methane. Now, there are lots of ways to get methane. Methane, natural gas, is one of the most common fossil fuel products that we get. We find methane pockets everywhere, especially as we're drilling for oil. But if we were trying to make small quantities of methane for a desired purpose, this would be a means to do so. So aluminum carbide, we do have to be concerned with it because of its water reactivity. It can create a flammable or explosive hazard when exposed to humid air because it is going to not only generate a flammable substance, it's going to generate a flammable gas. And so if we have a large quantity of it that is generating a large quantity of methane gas, we are going to see the results of that. Calcium carbide, we get that by mixing coke and lime. Coke, again, carbon-based substance, lime being calcium carbonate. And so putting those together in the electric furnace, we're going to end up getting calcium carbide, CaC2. This was one of the ways that we could make industrial grade acetylene. And I've heard stories. I've been teaching this class now for about 10 years. I have heard stories from students where they still more or less use this process for their home body shops and places. Use this as a way to generate acetylene for running, small acetylene torches and that kind of thing. So industrially, not used nearly as common. There are faster, cheaper, easier ways of getting acetylene, but this was a way to do it. It is water reactive. The water reaction creating acetylene, C2H2. So the reaction here is actually really pretty simple. Calcium carbide and water make acetylene and calcium oxide. Calcium oxide. So again, we see a double replacement reaction basically occurring here. The fruit of that double replacement reaction being acetylene, which is highly flammable. And when we burn acetylene, it burns with a very hot flame, which is obviously advantageous for the purposes of torches or welding equipment or whatever. But if we are not trying to make it intentionally, calcium carbide can be kind of a pain to store because of its reactivity with water vapor in the air. All right, let's turn our attention to some non-metallic substances that also happen to be flammable. So we spent a good chunk of the first part of this chapter looking at flammable metals, in particular the alkali metals, which are water reactive and flammable in air, and the alkaline earth metals, which aren't as reactive in air, but still are water reactive. And if we have the right kind of combination of stimuluses, we can get them to be air reactive as well. We're going to start here with phosphorus, though. So with phosphorus, we can create a chemical reaction between elemental phosphorus and oxygen to make a compound. That compound in this particular case is P2O5, diphosphorus pentoxide. Now that substance itself is water reactive and would make an acid solution. The acid in this case being phosphoric acid. So we covered this a little bit in the acids and bases unit on corrosives. The idea that metallic substances, when added to water, make bases, and non-metallic oxides, when added to water, make acids. And here we see yet another example of those. And so we are kind of getting both ends here of the flammability spectrum. We're getting flammable solids in the form of the elements. And then the products that they make are water reactive. And even though they don't form flammable substances when they react with water, remember the definition of dangerous when wet means that they can form corrosive substances with reaction with water as well, or they can form toxic or corrosive vapors. Well, this falls into that second half of that definition. The substance itself isn't flammable, at least not the oxide, and certainly not the phosphoric acid, but it is corrosive. And so while there are lots of nonmetals that are reactive, we're going to focus primarily on two of them, phosphorus and sulfur, because those are the two most common ones that we would see, and they are the ones that have the greatest danger and hazard associated with them. So we're going to start with phosphorus. Now, phosphorus has several different forms. Those forms are called allotropes. An allotrope is just another way that an element can configure itself molecularly and give it slightly different kinds of properties as it does. We are most familiar with the allotropes of carbon. Right now, you guys are using, well, some of you are using pencils. Pencils contain graphite, which is the most common allotrope of carbon. And the properties of graphite are such that it is slippery, which makes it a good lubricant, and it's a soft solid, which makes it really good for making, being like a pencil and smearing instead of scratching. The other most common form of carbon is diamond. Now, diamond is made up of the same stuff that graphite is. It's all carbon, but it's how the carbons are arranged that is different. In graphite, they are arranged in these rings, and they make sheets of these rings that slide over each other. And that's what gives graphite its lubricant kind of properties. In diamond, what we see is all of those carbons are network bonded to each other. So if you think about the Lewis structure of carbon, you know that carbon has 4 unpaired electrons. Well, if each one of those electrons goes out and pairs up with another carbon on each side, you have each carbon with 4 covalent bonds to other carbons around it. You do that enough times with a big enough sample, you're gonna have something that's pretty rigid. And that's why diamond has its particularly hard shape. And its very robust hardness as a property. So that's what allotropes are. And so we can see that different properties can come about as a result of different allotropes. Now, if we look at, there are 3 common allotropes of phosphorus. There is the white phosphorus, which is shown here on the left. This one we've already talked about at length at times. We're going to talk about it a little bit more here in a second. There is the red phosphorus here in the middle. This is the one that we most commonly associate with things like matches. And then there's this purple phosphorus here on the far right. That is actually the most stable form of phosphorus. And because of its stability, we don't actually use it very often because it's just not as reactive as we need it to be. We need a little bit of instability in a substance to guarantee that it's going to react the way that you want it to, especially in the case of phosphorus, where the whole point of phosphorus on a match head is so that you have something to burn. If the substance itself is too stable, it's going to require far too much energy to get that reaction started for that combustion. So Red phosphorus is certainly stable, but it's just unstable enough that simple frictional force dragging that match head across the side of the matchbook is enough to kickstart its combustion reaction. So white phosphorus. White phosphorus gets its name because it is white. It's kind of a waxy solid. It's kind of translucent. If you're unfamiliar with the term translucent, basically means that it's not quite transparent. You can't see clearly through it, but it's kind of got a little bit of you can kind of see through it. You know, think about really thick glass. You know, if you're looking through really thick glass, kind of from an angle, you can kind of see through it. You kind of have an idea what's on the other side, but it's not optically clear. White phosphorus is thermally unstable. On its own, just from sitting around at room temperature, it will gradually start to degrade and decompose to the red phosphorus allotrope. This transformation can actually be catalyzed by light, and that is why white phosphorus will often appear kind of yellowish instead of a pure white color. Because of its lack of stability, if it is exposed to air, it is pyrophoric, spontaneously combustible, and often in a very violent and potentially explosive way. The nature of the reaction itself produces products that are highly dangerous. White phosphorus itself is also extremely toxic. So ingested forms of white phosphorus have been known to cause severe liver damage. White phosphorus on its own is very lethal and highly unstable. Which makes it very difficult to work with and very difficult to store. However, one advantage that it does have is that it is insoluble in water. And because of its lack of solubility in water, that is usually how we store it if we have it in bulk form. However, from a transportation standpoint, if we were to transport it from one place to another, we would not store it underwater. How it would go instead is basically we would melt it and transport it in heated containers. So that's white phosphorus. Again, the most unstable, the most unfriendly, toxic version of the element. Now, by comparison, red phosphorus is going to seem really, really stinking benign. We know red phosphorus as kind of this really dark red powder. We also know that it is the intermediate phase between white and purple or violet phosphorus. On its own, at normal conditions, it is very shelf stable. In fact, it's not going to catch fire at temperatures under 260 degrees Celsius. So that is the exact opposite of what we would consider pyrophoric. Or pyrophoria occurs really pretty much any time we can expose a flammable substance to room temperature air and it immediately combusts. Where it does have flammability is when we provide it with a little bit of an energy boost. And that energy boost comes most frequently in the form of friction. And so this is why we will find red phosphorus used in a lot of things that are flammable when we have to strike them in some kind of way. So kind of go back through your mind and think about some of those things. Matches we already talked about. Flares, either road flares or like railroad flares. Those are going to have phosphorus as their base. It's also why they tend to burn with that reddish kind of color. That's a dyeing agent usually that is put in them, but the phosphorus itself contributes in some ways. Cap guns. You ever played with those small cap gun fireworks? When you were a kid, those little caps that you'd put into your toy gun and help them make a loud sound. The friction comes from the hammer coming back on that gun and smacking into that firework. The actual explosion, the firework itself, phosphorus based. Which is also why it kind of had that smell that you'd get when you set them up. Phosphorus is also used in the creation of methamphetamine agents, both from the pharmaceutical standpoint as well as from the non-pharmaceutical standpoint. And so that is one of the agents that is used in making those substances. And it's also one of the reasons, there are a couple, why obtaining red phosphorus is becoming a harder thing to acquire. In fact, our department hasn't ordered phosphorus for quite a while now because there is a scarcity and a price issue associated with it. So not today, but I think next week's lab, you'll be doing fire and some different types of fire, and you'll get to work a little bit with phosphorus, I think, in that lab. You'll notice we don't have a whole lot of it. And that's one of the reasons. Sulfur. Sulfur is interesting in the sense that it exists as a molecule, and that molecule is an 8-membered ring. So what we have is 8 sulfurs that are bonded to each other, and they form this what is called a cyclic crown. Basically, from a 3-dimensional standpoint, that ring has an up, down, up, down, up, down configuration. And so if you think about it, you're going up, down, up, down, up, down in a circle. It's going to kind of look like a king's crown. On its own, sulfur can create really pretty crystals. We can see some of those here. And the sulfur itself really doesn't have an odor on its own. The smell that we associate with sulfur is not sulfur itself, but rather the byproducts of some of the reactions that sulfur makes. So when you go into an area, oh, it smells like sulfur in here, it's so terrible. It's not actually sulfur, elemental sulfur that you're smelling. It's a sulfur-based compound. Some things we know about sulfur. Naturally, we can find it in lots of places on Earth, especially near hot springs, especially near places where there's known volcanic activity. So most common regions for that are places like Hawaii, like volcanic islands, other places in that Pacific Ring of Fire, where there again is known volcanic activity. Places like Yellowstone National Park, where you've got your basically a national park on a gigantic volcanic site that is largely dormant, but you still have hot springs there. You still have you have geysers and other things as well. Sulfur easily melts, easily sublimes. Temperatures here 100 Celsius, that's the boiling point of water. Sublimation also occurs very easily. When we burn it, the smell of burning sulfur is the result of something called sulfur dioxide. Sulfur dioxide has the smell of burning hair, burning rubber. It's a very powerful, kind of knocks you on your backside kind of odor. It can be very choking odor if you get it in a high concentration. Sulfur is also a component in black powder. Black powder being a mixture of saltpeter, potassium nitrate, charcoal, just plain old carbon, and sulfur. On its own, sulfur will not dissolve in water and is not a toxic material. But as we can see from these middle two bullet points here, well, middle three, it's pretty flammable. And that's where its hazard lies. It's a flammable substance. And if we put it in the right combination of things, again, black powder being one of those combinations, we can get something that borders on the explosive end of the spectrum instead of just the flammable end. Now, the other byproduct of sulfur reactions, and the thing that we probably associate the most with a sulfury smell, sulfur dioxide is certainly part of that. If you go to an active volcanic region, that sulfur dioxide smell is going to be one of those things that you smell. It's why a lot of, if you go to a place like Old Faithful or something like that, it's the smell that's going to kind of permeate everything there because of the volcanic activity. But the other thing that we often associate with sulfur is that kind of swamp gas smell. That smell of rotten eggs, of raw sewage, that's hydrogen sulfide, H2S. And H2S is also a flammable gas. But that smell, that combination of odors, that's what we usually associate with sulfur. But it's important to know, sulfur itself doesn't have an odor. It's the byproducts of sulfur, the results of its reactions that do. All right, I'm going to close out with two more water reactive substances. The first ones, the ones that produce hydrogen chloride gas, which can then be converted into hydrochloric acid. In hydrogen chloride, we have a toxic gas that is very, very irritating. One of the reasons it is so irritating is because if it encounters your body being mostly water, that hydrogen chloride gas is going to turn into hydrochloric acid, and it's going to burn like crazy on whatever it touches. You accidentally get too close to a bottle of hydrochloric acid, especially a concentrated hydrochloric acid, and you breathe in too heavy and get a real good sniff of it, your nose is going to start burning from the hydrogen chloride vapor coming off of that acid and interacting with your nose, and basically you just inhale a small amount of hydrochloric acid, and it doesn't feel good. Hydrochloric acid is a corrosive liquid. It is not terribly toxic in its aqueous form, but it does burn the snot out of you. Hydrogen chloride has a very pungent odor, a faint chlorine kind of smell to it, but mostly it's just kind of a strong odor. Because of its strength, it has a suffocating kind of quality to it, and it can form fumes in the air, which can kind of make the air hazy and a little bit difficult to see in if there's a high enough quantity of those vapors. Now, there is a long list here of substances that can do this kind of chemical action. Don't bother trying to write all of these down. They're all in your textbook. But what we can see here, primarily what they all have in common, is that they are substances that include chlorines. Now, that's not to say that every chlorine substance that exists will create hydrogen chloride, but the ones that are highly reactive tend to do so. Another thing that we'll see is that some of these here are anhydrous. Remember, anhydrous means that they have had water removed from them. So these anhydrous forms are going to be especially water reactive, because to be anhydrous, again, means that we've had to remove the water from them, which means that they are also very itchy to get that water back. And when they get that water back, we're going to see those reactions taking place. And so we've got a mixture here of metallic chlorides like aluminum and tin 4 and titanium 4 chloride. And we've got a mixture of non-metallic chlorides like phosphorus oxychloride, phosphorus trichloride, and chlorosilanes, to name a few. The last thing that we want to talk about are the substances that will react and give us acetic acid vapor. Now, acetic acid is the substance that is what gives vinegar its smell. It is not a terribly strong acid, but it does have an odor to it that we know very well. That's the odor of vinegar. Now, in low concentrations, that vinegar odor isn't going to be terribly difficult or hard to manage. But in high concentrations, that acetic acid vapor can be very suffocating because it can be very strong and pungent. And if it gets too exposed to your eyes or exposed to your nose, it can have a very irritating quality to it. Now, some of the substances that react to give us this vapor include acetic anhydride and acetyl chloride, which are both organic products. And those substances on their own are corrosive irritants. So if those substances, which are the precursors, get into your skin, get into your eyes, they can cause severe burns in those areas. And the main reason why is, again, your body is mostly made out of water. And what happens is that those substances, when they come into contact with your body membranes that have some water-like qualities to them, they will convert into high concentration acetic acid. And high concentration acid of any kind, even if it is a weaker acid, is going to have an effect on your body. And that effect is going to be negative, irritating, and potentially hurtful, or if in the right combination, damaging enough to really impact your quality of life. Acetic anhydride is a colorless but fuming liquid. Where we see it used most often is in the production of aspirin. Now, aspirin in this case that we're talking about is aspirin, like Bayer aspirin, not acetaminophen Tylenol, not Advil, not Motrin, but actual aspirin. We can also see it used in cellulosic acetates and some other products as well. Its primary hazard, in addition to its fuming nature, is the ability to form acetic acid when it reacts with water. And then finally, acetyl chloride. Acetyl chloride is also a colorless and fuming liquid. We find it used primarily in the chemical industry. It is a great precursor product for a lot of organic substances. It reacts violently with water, and in that formation of water, we get two acid vapors. We get acetic acid vapor and we get hydrochloric acid vapor. What's particularly dangerous about acetic chloride, in addition to forming all of these corrosive agents, it's also very flammable. So it's got a low flash point. It is a risk for fire and potential explosion depending upon the circumstances. So that's all for chapter 9 here. And so when we pick up again with this on Monday, what we will do is we will start looking at toxic materials out of chapter 10. Have a great weekend.